Hello and welcome. Previously, in the last episode, we began exploring the idea of entrapped space-time manifolds existing inside one another. The idea builds from the observation that black holes, being one form of entrapped space-time manifold, exist inside our universe. By studying what the Kerr metric solution tells us about the internal structure of a rotational black hole, we look to propose a brand new interpretation by considering the idea that the pair of child universes born from the associated white hole are themselves entrapped manifolds inflating inside our universe. In the last episode, we contemplated this idea from the point of view that our universe is inflating inside a much larger parent universe we call the Subverses. In doing so, we found that such a simple solution could give answer to four of the fundamental mysteries of cosmology, namely, why is the universe flat? What created the large-scale anisotropies in the cosmic microwave sky? How the cosmic microwave background dipole came to be? And what happened to all the antimatter created at the time of the Big Bang? In this episode, we apply the exact same idea of a child universe entrapped inside its own manifold, inflating forth from a black hole inside our own universe. By doing this, we will be met with a wholly revolutionary vision of what dark matter may actually be. Or, to put it another way, ask, then answer the question. After 40 years of searching for a dark matter particle, what has been found? Very little would be my answer. So why not try a different approach? An approach based on general relativity instead of quantum mechanics. In doing so, we shall begin to see how this one singular idea of entrapped manifolds may be able to give answer to the question, what actually is a particle? Previously, we had applied this idea to considering the expansion of our universe into the surrounding existing vacuum of a much larger parent universe, the Subverse. As our universe is shaped by the surrounding local curvature of the Subverse, and because the curvature of the surrounding vacuum of space is flat, means the curvature of our universe is also flat. We measure and observe a flat universe because our universe is an entrapped manifold expanding out into the vacuum space of our surrounding parent universe. A simple answer to a fundamental mystery of cosmology in considering applying this idea to our universe, where our universe is the child universe and the Subverse is the parent universe. Now, in applying the exact same idea of two entrapped manifolds inflating forth from a rotational black hole, where said black hole is inside our universe, then what would be the resultant outcome? Dark matter would be my answer, plain and simple. Rather than dark matter being like baryonic matter in that it is made up of individual particles, let us try a different approach, one born out of general relativity as opposed to quantum mechanics. Maybe, as heretical as it may sound to a particle physicist, particles are not the most fundamental things in physics, but rather the fractal geometry of entrapped conformal space-time manifolds is more fundamental. Or rather to say, what does it physically mean for one entrapped manifold to exist inside another entrapped manifold? What does it physically mean for an entrapped manifold, such as a child universe, to be inflating inside a parent universe, both coexisting spatially but not temporally, each with its own arrow of time? As an observer inside our universe, how would such a child universe be made physically manifest? Us, here on Earth, what are we able to observe of such child universes? To provide a concrete example, our galaxy, the Milky Way, is surrounded by a dark matter halo. In the context of our idea, this dark matter halo is composed of two child universes. These pair of child universes we call subverses, or subverse, in reference to a single child universe. I use the prefix sub to denote that it is part of our universe, being entrapped and inflating inside it. In the case of two child subverses that form the dark matter halo, these are spatially located in the intergalactic void that surrounds the Milky Way galaxy. The associated black hole that gave birth to this pair of child subverses is naturally the supermassive black hole we call Sagittarius A star, which dwells at the center of our own Milky Way galaxy. So, as an observer here on Earth, what does the existence of being surrounded by two child subverses mean? These two colossal child universes, each with a radius of around 50,000 light years each. One analogy immediately comes to mind. The analogy of Schrödinger's cat. A cat is sealed inside a box. Inside the box with the cat is a contraption. Inside the contraption is a Geiger counter that waits to measure the decay of a radioactive atom next to it. The Geiger counter is wired to break a vial of poison upon detection that the radioactive atom has decayed. If the atom does decay, the vial of poison is broken, which in turn kills the cat. On the other hand, if the atom does not decay, the vial is not broken and the cat lives. Sealed inside the box as an external observer, we have no way of knowing whether the cat is dead or alive. Using the analogy of quantum mechanics, we say that the cat exists in a superposition state of being both alive and dead at the same time. However, rather than a box, that box is the entrapped manifold that is the child universe inflating forth from a black hole. Trapped inside the enclosed manifold, The cat exists along with the Geiger counter contraption. This space-time manifold has its own arrow of time through whose passage one of two possible outcomes can occur. The first outcome is triggered by the decay of the radioactive atom. This decay is detected by the Geiger counter, which in turn smashes the vial of poison that in turn kills the cat. The second outcome is that the radioactive atom does not decay, meaning that the vial of poison is contained and the cat goes on living. Us, as an external observer of this entrapped manifold, exist in upon the space-time fabric of our universe with its own emergent arrow of time. We, unable to see or detect the cat, are unable to tell whether the cat is alive or dead. So rather, we say the cat exists in a superposition state of being both alive and dead. Though, as a note, being a cat lover, I naturally root for the cat being alive. Of course, our consideration of an entrapped child universe comes from studying the mathematics of general relativity and what the Kerr metric solution tells us about the structure of a rotational black hole. It did not come from the study of particles at the small scale, the quantum scale, via quantum mechanics. So how could the two be related? If there is one axiom seared into my mind, it is the dictation of fractal geometry, in that self-similar patterns repeat, irrespective of scale. That is, inside a fractal pattern, the same pattern repeats itself, either in part or in whole, at different and multiple levels of scale. So, although our example of a pair of child universes are in relation to forming a dark matter halo about the Milky Way galaxy is at the astrophysical scale, the same pattern can repeat itself down at the quantum scale. That is how the two can be related through the mathematical law of fractal geometry, in that self-similar patterns repeat, irrespective of scale. So, from this simple consideration, I feel helps open a window into the most fundamental aspect of nature. Maybe the world of radioactive decay is itself existing in an entrapped manifold whose arrow of time is separate from our own, but whose spatial volume exists inside our own. After all, radioactive decay is invariant to our arrow of time as we observe it. Never mind the whole problem of non-locality that has plagued quantum mechanics from the beginning. So that is one analogy or insight. Another analogy comes in thinking about how and why the child universe can be thought of as being exactly like the parent universe, except for one of scale. That is to say, as an observer in either the parent universe or the child universe, we would see a universe full of galaxies, each populated with hundreds of millions of stars. The epistemology that gives vision to this lies in our aforementioned axiom that self-similar patterns repeat irrespective of scale. In developing the Big Bang Kilonova Hypothesis, I imagine the parent Subverse as being exactly like our universe, except for one of scale. It is a universe where stars are born, die, and in turn able to give birth to dense stellar cores, such as white dwarfs, neutron stars, and even black holes. In fact, my initial evolution of the idea was to use a core collapse supernovae as a template for the Big Bang before realizing a kilonova was a perfect fit of the large-scale anisotropies seen in the cosmic microwave sky. In imagining a child universe inside our universe, we apply exactly the same logic as self-similar patterns repeat, irrespective of scale. This child universe we imagine as being full of galaxies populated by hundreds of millions of stars, but the exact reason for why the child universe is a much smaller universe in comparison to the parent comes in understanding what exactly a black hole does. What the black hole does is crush down the metric spacetime fabric of the parent universe. This crushing down of our universe by the black hole can be seen in considering what happens as an object falls in towards a black hole from the point of view of an external observer. Here we consider a probe which emits a regular flash of blue light as it falls in towards the black hole. An astronaut in orbit around the black hole acts as an external observer. The metric distance of space as we approach the black hole becomes smaller and smaller. A meter ruler will become compressed down as the space-time fabric is crushed by the black hole. The infalling probe will become smaller and smaller, not because it is magically shrinking, but because the very fabric of the universe is crushed by the gravitational field of the black hole. The probe, a meter in diameter, is still a meter in size, but because of length contraction arising from the theory of general relativity, it is crushed down. Our astronaut sees this length contraction in how the blue light emitted by the probe becomes increasingly red-shifted. A photon emitted from the probe traveling towards the external observer has an initial wavelength in the blue end of the spectrum, but as it travels away from the black hole and towards the astronaut, the wavelength of the photon expands as the fabric of spacetime expands. Initially blue, the photon will change color, becoming green, yellow, orange, and then red, as its wavelength expands with expansion of spacetime as it travels away from the black hole. The photon is redshifted from the blue end of the spectrum through to the red end because of the expansion of spacetime as we travel away from the black hole. Traveling towards the black hole, the probe undergoes length contraction as the metric of space is crushed down to nothing at the event horizon of the black hole. It's not only the metric length of space that is crushed by the weight of the black hole, but time itself becomes dilated as space contracts. The regular flashes of light from the probe become longer and longer when observed by the astronaut. Close to the event horizon, a single second of time, from the probe's point of view, could be a year for our external observer, the astronaut. This crushing and stretching out of space-time becomes so extreme near the event horizon that the difference in the gravitational pull between the probe's side facing the black hole and the side facing away from it causes the probe to become elongated and spaghettified. The probe undergoes spaghettification as it crosses over the event horizon. Now, as we discussed in the previous episode, that with rotation, the singularity at the heart of the black hole is spun into a ringularity, opening up a wormhole. However, instead of pretending that this wormhole is a magical doorway into another universe, completely separate and removed from our own, we rather say that the child universe it leads to is actually still located in our universe, coexisting spatially within it. Explicitly, we say that these pair of child universes are inflating forth from both poles. One child universe inflates from the North Pole, and one other child universe inflates forth from the South Pole. So rather than the inevitable fate of falling onto the black hole's singularity, our probe rather passes through the wormhole and then back out into either one of the child universes. Now, as we've seen, the metric scale of the probe was contracted down as it approached the black hole. In totality, all the space-time fabric and objects consumed by the black hole have their metric scale contracted down by the black hole. What exactly happens inside the black hole is physically beyond our sight. Using mathematical inference via solutions of relativity gains us insight. However, a topic we shall repeatedly come back to in future episodes, let us constrain ourselves to what we can observe back outside in our universe. But to say a large part of my reasoning is in seeing how a field, be it the continuum of the space-time fabric or a quantum field, are one and exactly the same thing, except for one of scale. Theoretically, this builds upon the proposed duality between conformal field theory and anti-de Sitter spacetime, the discussion of which we will unpack in future episodes. The main point I am trying to make is that in totality, we could consider the function of a rotational black hole as being a scale transformer. In considering an object falling in towards a black hole, we see how the object's length is scaled down because the fabric of the fields that make up the physical probe are themselves crushed and scaled down by the ringularity at the heart of the black hole. The output, we can imagine, is the probe scaled down, exiting out into either child universe, following the probe's gravitational slingshot around and through the ringularity and out into said child universe. The resultant output being the probe existing inside the child universe exactly the same except for one of scale. Where the probe might have been originally 1 meter in diameter, it now measures a micron in diameter. The reason the probe scale has changed is because the physical fields of the parent universe have effectively been scaled down from their passage through the black hole and its associated ringularity. Now, of course, the reality, I would say, would be more like the probe will be spaghettified and then atomized before these atoms in turn are turned inside out. The information of what the probe was becoming part of both child universes would, I feel, be a much more accurate statement. But as a simple analogy, we can think of the black hole as being a scale transformer. The input, the fields of the parent universe operating at their given scale, the black hole acting as a scale transformer in turn outputs the same fields after crushing their metric scale down. The resultant child universe being an exact copy of the parent universe, inheriting its physical fields, except for one of scale, as self-similar patterns repeat irrespective of scale. The end result is that the pair or child universes, we can suppose, are like its parent universe, operating by the same rules of physics except for one of scale. Then, in turn, just like our universe is expanding into the spatial volume of our parent universe, so are these child universes expanding inside our universe. Having now discussed how physical objects are scaled down by length contraction due to falling into a black hole, such that they fit inside a child's universe, let us more generally consider the physical quantum fields themselves in terms of the density of vacuum energy. In quantum mechanics, the idea of vacuum energy arises from quantum field theory, the vacuum energy being the lowest possible energy state of said field. The general idea is that quantum fields are omnipresent, and down at the quantum scale, particles such as the photon and electron are excitations or ripples upon said fields. These fields vibrate, causing the formation of temporary or virtual particles to pop in and out of existence inside a vacuum. The energy of these vibrations is what we call the vacuum energy. So if we imagine a cubic meter of vacuum in the depths of space and look to see what is inside, the idea of vacuum energy is that there is not nothing inside. Rather, the physical quantum fields inside that volume of vacuum are vibrating and fluctuating. Down at the quantum scale, which is from 1 femtometer to 1 nanometer in scale, we would see virtual particles coming into and out of existence arising from the vibration of the field. This vacuum energy, or zero-point energy, as it is also called, represents the effective ground state of our universe. With this idea in mind, let us consider how the density of this vacuum energy changes as this cubic meter of vacuum falls in towards a black hole. Just like our probe underwent relativistic length contraction as it fell into the black hole, so too does our cubic meter of vacuum. As the vacuum becomes contracted, so too does the density of the vacuum energy inside our cubic meter of vacuum. In effect, the ground state of the universe is raised up by the relativistic length contraction caused by the presence of the black hole. In conjunction with relativistic length contraction, there is also time dilation of our cubic meter of vacuum. A second close to the black hole would be a year for our external observer, the astronaut. As we approach the event horizon of the black hole, the surrounding temperature drops, and then at the horizon itself, it is only 100 millionth of a degree above absolute zero. One could imagine the fluctuations of the field slowing down as they become frozen in time caused by the relativistic time dilation from an outside observer's point of view. Following the equivalence principle from the point of view of our cubic meter, it would fall through the event horizon, its field still fluctuating with virtual particle pairs popping into existence. However, whether these virtual particles then pop out of existence just as they had appeared at the black hole's event horizon might not be the case. Hawking radiation is a result of virtual particle pairs being created at the event horizon of the black hole. A virtual particle pair that are entangled is created at the event horizon of the black hole. One particle falls into the black hole and the other escapes out into the universe. Normally, a virtual pair of particles will quickly come back together, annihilating each other. The energy consumed from the field to create said virtual pair of particles is given back to the field by their annihilation. But for a pair of virtual particles on the edge of an event horizon, where one falls in and the other escapes, implies that they are unable to ever meet up again in the future. One virtual particle stays inside our universe, and the other virtual particle falls beyond the bounds of our universe into the black hole. The virtual particles inside our universe stops being virtual and becomes an actual particle. We call these particles being emitted by the event horizon Hawking radiation. The energy borrowed from the field is taken from the black hole itself. It is this carrying away of energy by particles of Hawking radiation in the form of thermal energy that causes the temperature around the event horizon to drop to near absolute zero. As mass equates to energy, it implies that the creation and emission of Hawking radiation by the black hole causes the black hole itself to lose mass. Over the course of hundreds of trillions of years, a black hole will very slowly evaporate, losing all its mass through evaporation by Hawking radiation. The black hole information paradox arises from the conflict about Hawking radiation. Objects, such as our probe, that have fallen into and become entrapped inside the black hole contain quantum information about what the probe was. The probe falls in, gets vaporized, But by the laws of quantum mechanics, this process is time reversible, meaning even vaporized, we could theoretically reverse this process, and by using the encoded quantum information, we could be able to reconstruct the probe. However, the Hawking radiation created at the event horizon does not contain any information of any object that has previously fallen into the black hole. So as the black hole evaporates, any information of what the probe was is then inevitably lost. It is this loss and destruction of information that violates the most fundamental law of quantum mechanics, which requires unitary of the probability wave. Unitary of the probability wave implies that information can never be destroyed. But because of Hawking radiation, information is lost, and theoretical physicists have spent the last 50 years trying to find an answer. Returning back to our consideration of our original cubic meter of vacuum falling down into the black hole. Like the probe, we imagine our metric cube of nothingness being contracted down before exiting through the associated white hole into the child universe. Just like the probe was crushed down to, say, a micrometer cube in size when compared to its original size, the cubic meter of vacuum has also been crushed down and exists as a micrometer cube in size inside the child universe. In effect, the ground potential energy of the quantum fields inside this vacuum, which was originally contained in a cubic meter outside in the parent universe, has now been scaled down, compressed, and entrapped inside a micrometer cube existing inside the child universe. Now, if you have made it thus far in my humble presentation, please give yourself a well-deserved pat on the back. Truly, you deserve it, as we now step into the land of new physics. Of all the arguments that I have to make, this is probably the single most fundamental argument and probably the hardest. This argument that the ground potential of a child universe in comparison to the surrounding parent universe is so much higher. But beyond that, I would extrapolate this idea out into seeing how, with each decreasing scale of a given field, the greater the density of energy in that field does become. There is a reason why E equals mc squared, and here is the root of that fundamental reason I believe. There is a reason why the vast majority of mass, as we know it, in the form of baryonic matter, comes from the massless gluon entrapped inside the manifolds of the proton and neutron, as self-similar patterns repeat irrespective of scale. But in my haste, I get ahead of myself. In developing our Big Bang Kilonova Hypothesis, I borrowed an idea in regards to the Higgs boson called the Big Rip. The current Big Bang story, described by mainstream cosmology, describes how the Higgs field comes into existence as the temperature drops below 10 to the power of 15 Kelvin, causing a phase transition such that the electroweak force splits into the electromagnetic and weak forces. This phase transition and bifurcation of the electroweak force into the electromagnetic and weak forces, creates the Higgs field, which acts as a thick soup or gravy upon certain particles, such as the proton and electron, giving them mass. Prior to this phase transition, electrons and protons could move faster than the speed of light. But once the Higgs field comes into existence, these particles can no longer move faster than the speed of light. Inflation theory describes how the universe expands faster than the speed of light in its very initial moments before then stopping. The reason why it stops expanding faster than the speed of light is because the Higgs field comes on and fermion particles with a half-spin gain mass. Current measurements suggest the Higgs field might be in a metastable state, implying that the field might not be at its lowest possible energy state. That is to say, that there may be a lower vacuum energy state in which the Higgs field might exist. At the moment, the Higgs field exists in this higher vacuum energy state in comparison to this lower vacuum energy state. The idea of the Big Rip comes about from the suggestion that the Higgs field might find a way to quantum tunnel its way from the higher vacuum state to the lower vacuum state, the ultimate effect of which is that the fabric of our universe comes apart as particles no longer have mass and the space-time fabric rips itself apart. So, that in a nutshell is the idea of the Big Rip. It is this description of the Higgs field in being in a metastable vacuum whose energy level is higher than the actual minimum that I apply in trying to figure out what differentiates our universe from the surrounding parent universe, meaning the vacuum energy of our universe is in a higher state than the surrounding parent universe. Our parent universe, the Subverses vacuum energy, is much lower in comparison to our own universe. The reason why comes in our aforementioned examination of how the associated black hole contracts and compresses the fabric of our surrounding parent universe down before being thrown out into our universe, the child universe of the superverse. Another point is that the flow of spacetime at each of the event horizons is at the speed of light. At the event horizon of the black hole, the flow of spacetime is at the speed of light in towards the ringularity. At the event horizon of the white hole, the flow of spacetime is at the speed of light out and away from the ringularity. Below the event horizon of the white hole, the expansion out is faster than the speed of light. Above the event horizon, the flow of spacetime is less than the speed of light. In recognizing the phase transition from the white hole and into the child universe, the idea of the Higgs field fits perfectly into place. The Higgs field turns on in the Big Bang Kilonova model at the event horizon of the white hole. Ejected from the white hole, fermion particles, electrons and protons gain mass as the Higgs field comes into existence, giving form to our universe, acting as the glue that holds us, the child universe, together inside our much larger parent universe. Having mentioned Hawking radiation and its creation at the event horizon of the black hole, wherein we can see it tearing the fabric of our universe, is met with its symmetrical opposite at the event horizon of the white hole, namely that the Higgs field of a child universe turns on at the event horizon of the white hole that gave birth to it. This then acts as the glue which holds said child universe together inside a much larger parent universe. This creation of a metastable vacuum energy within the child universe arises from how the black hole in the parent universe compresses its fields down, raising the vacuum energy density, which is then entrapped inside the child universe. A reverse Hawking radiation, if you will. In fact, the definition of what a white hole is that it is a time-reversed black hole. So with Hawking radiation, as we saw, a pair of virtual particles are created. One particle falls into the black hole and the other escapes out into the universe. Reversing this story backwards, one virtual particle travels towards the event horizon of the white hole from the outside, and the other virtual particle travels towards the same event horizon from within the white hole. The two virtual particles meet on the white hole's event horizon and annihilate each other, i.e., Hawking radiation in reverse. The twist in the tail in specific consideration to our idea of entrapped manifolds is that the event horizon of the black hole and the event horizon of the white hole are one and the same structure. The white hole we explicitly place at the polar regions of the black hole's event horizon. Looking at it in full, we have the creation of a pair of entangled virtual particles at the event horizon of the black hole. One particle is escaping out into the universe, while the other is falling down towards and through the ringularity. The particle trying to escape out into the universe will inevitably do many orbits around the outside edge of the event horizon before escaping out into the universe. The other particle travels down and through the ringularity and then back up through the white hole to exit spatially back outside in the parent universe as part of the new child universe. Being entangled virtual particles, they meet again at the event horizon of the white hole, which is itself a part of the black hole's event horizon, cancelling each other out and giving back the energy borrowed from the mass of the black hole. So, about that black hole information paradox, or war, as Susskind termed it, that has raged for over 50 years. Damn, that was easy for us to resolve. Another key factor is we need to consider how the temperature at the event horizon of the black hole is near to absolute zero. Vampiric-like, the black hole sucks the temperature and energy out from the parent universe. This cooling effect comes about due to the creation of Hawking radiation, the thermal energy carried away by the creation of virtual particle pairs, where for a time they become real. The behavior of a black hole is analogous to a waterfall, where falling off the edge is equivalent to falling into the event horizon. I would ponder that temperature inside the black hole takes a plunge over the edge, meaning the temperature inside the black hole drops below absolute zero. Or rather, because the scale of the quantum fields are being compressed down, so too is the amplitude of vibration of said field is compressed and shrunk. With our original cubic meter of vacuum, imagine a wave of a field. The amplitude of this wave is half a meter, meaning a whole wave form fits inside our meter cube. Traveling through the ringularity and out into the child universe, said cubic meter becomes a micron in size. Hence the amplitude of the wave is now half a micron in length. Overall, the vibration of the quantum fields determine the temperature. The greater the vibration, the greater the temperature. The smaller the vibration, the lower the temperature. As the vibration of the field inside the child universe is so much smaller than the equivalent field of the surrounding parent universe from which the child is derived, it would imply that the child universe is a much colder place relative to the parent universe, meaning that the child universe would effectively be cold and inert with respect to the parent. Now, whether the child universe exists below absolute zero or not is a matter for another time. The point I am trying to make is why dark matter is in fact called dark matter. After all, at the beginning of this episode, I equated child universes inside our own universe, these subverses, as being equivalent to dark matter. The CDM in lambda CDM stands for cold dark matter, and from this precursory examination of this idea of ours, these entrapped manifolds, we can see how and why the dark matter is called dark matter. So in trying to answer the question, what does it physically mean for a child universe to be inside a parent universe, both existing spatially but not temporally, then our answer could be to say it is called dark matter. Not interacting with the baryonic matter of the parent universe, as the fields of the child universe operate at a much smaller scale than ours. Same laws of physics, but each verse operates independently at its own scale. Working at their own scales, the parent and child universes coexisting together. Overall, the child universe is held together inside the parent universe by the raising of the ground potential of the child universe's Higgs field with respect to the parent. However, like mass in baryonic matter coming from the entrapped gluon, so does the child universe have mass inside the parent universe from the energy entrapped within said child universe, hence cold, dark, and inert, that has the presence of mass inside of the parent universe. Putting it all together, let us now consider how we came to live in a universe filled with cold, dark matter, and it starts with the creation of supermassive black holes. As for how supermassive black holes came to exist in our early universe, The Big Bang Kilonova Hypothesis has a very simple explanation for this. Fragments from the neutron stars of the superverse, after being length contracted by the ringularity that gave rise to the Big Bang Kilonova. A full explanation for yet another time, but, as suggested, the reason for mentioning supermassive black holes allows us to come full circle in explaining the formation of cold dark matter as we apply our idea of two entrapped manifolds inflating forth from a rotating black hole. Observations by the James Webb Space Telescope have confirmed the formation of massive galaxies in the very early universe, more affectionately called little red dots. These galaxies existed some 600 million years after the Big Bang. What is more, these galaxies have been observed as containing supermassive black holes inside them. So as a matter of observational fact, we know that spiral galaxies had already formed some 600 million years after the Big Bang, and at their center resides a supermassive black hole. Now, as it has made every headline in the cosmological press, a study by Lionel Shamir of these spiral galaxies shows a striking difference in the number of galaxies whose spiral arms rotate clockwise versus counterclockwise. Although a small sample size of 300 galaxies, more than 2/3, had a clockwise rotation, and only a third had a counterclockwise rotation. In an isometric universe, the split should have been half and a half. Now, to quote Google AI, this observation has led to speculation about the early universe and the potential influence of a preferred axis of rotation, inherited from a rotating black hole, according to a theory proposed by some scientists. Ground zero for the Big Bang Kilonova Hypothesis is my podcast episode, where I first present the idea of using a kilonova as the causal mechanism for the Big Bang. In that episode, I present Lionel Shamir's earlier work, where he showed the Spinward asymmetry from a study of around 20,000 galaxies that are about 1 billion light years from us, as opposed to this later study of 300 galaxies from the very early universe. The dipole and quadrupole maps of Spinward asymmetry from the earlier study are an exact match for the dipole and quadrupole maps of the cosmic microwave background radiation. For a long time, I've wondered why Shamir's work has not been either reproduced or shown to be in error, as yet again the entire theoretical cosmological community ignores the observational evidence. Stop it! I am supposed to be on my best behavior, but yet again the observational evidence is on our side of the argument, and in this game, observational evidence is king. And now we move to checkmate. Supermassive black holes existed from the moment of the Big Bang, from the point of view of our model. The early universe, the Higgs field turned on, is a homogeneous plasma of protons and electrons, filled with the fragments of the superneutron stars, these now supermassive black holes. What do these supermassive black holes do? They feed. So we now apply our idea of a pair of entrapped manifolds growing forth from these rotational supermassive black holes. Firstly, the primordial plasma will be spun out into forming an accretion disk as a quasar is born. Secondly, fueled by the infall of primordial plasma of the early universe, these pair of child universes, or subverses as I call them, grow. One subverse from the North Pole and another subverse from the South Pole. As nothing can travel faster than the speed of light inside our universe, so too is the rate of expansion of these child universes inside our own constrained, meaning we can put an upper limit on the rate at which these child universes expand inside our own universe. Because of the rate of consumption by the supermassive black hole, coupled with this speed limit constraint, forces the child universes to expand out with spherical symmetry, at least initially at the very start. As a note, I explain in depth in my pieces Anatomy of a Kilonova and The Microwave Story why spherical symmetry is so important, as it is a prerequisite in order to derive Friedmann's equations describing an expanding universe within the framework of general relativity. The other critical importance of spherical symmetry in the early expansion of these child subverses inside our own universe is that each of the two subverses push down on each other as they expand. As a whole, the two child subverses expand with spherical symmetry outwards, but as the northern subverse pushes downwards and the southern subverse pushes upwards, it forces the matter falling into the black hole to become sandwiched in between. This further flattens out the accretion disk, leading to the formation of a proto-spiral galaxy in the very early universe. Ordinarily, I would say that dark matter does not interact with ordinary matter for the reasons we have so carefully discussed. But just like our universe has a parallel twin universe composed of antimatter to us, so too are these pair of child subverses, each the parallel opposite of the other. This follows from the law of CPT, charge, parity, and time symmetry, and follows directly from Andrei Sakharov's description of a 2D didactic cosmological model in considering both baryon asymmetry and CPT symmetry, an idea that has been the focus of many cosmological models, including recently Neil Turok's latest model. In our model, our parallel universe of antimatter is growing in the polar opposite direction to the expansion of our universe within the superverse. Following the same pattern, the matter inside the northern subverse would be antimatter to that inside the southern subverse, and vice versa. The fields, like the electromagnetic field inside each of the subverses, are derived from our fields, and thus interaction between the northern and southern subverses would be conveyed between them via our fields back outside in the parent universe. This interaction, I argue, causes the matter to become sandwiched in between, leading to the formation of spiral galaxies. In fact, I would go further and say we can see evidence of this interaction today inside our own galaxy being conveyed upon the electromagnetic field. Radio observations of the Milky Way's galaxy core show filaments aligned with our galaxy's poles. Aligned with the polar axis, they are magnetic, synchrotron-emitting structures spanning up to 150 light-years in length, which were observed with the Meerkat telescope. They consist of relativistic electrons spiraling in strong magnetic fields. This synchrotron radiation is usually associated with neutron stars and magnetars, which have powerful magnetic fields. But here we have these structures spanning over 100 light-years in length inside our Milky Way galaxy. Not only have they been seen in our galaxy, but they are found in other galaxies as well. Evidence of extremely powerful interaction between the two subverses, of which our galaxy is sandwiched in between. In addition to this, there is actual matter and antimatter annihilation. Electron and positron pairs annihilate each other with a very unique signature of 511 kiloelectron volts, which lies in the gamma ray end of the spectrum. Observations of our galaxy's core by X-ray telescopes like Fermi and eRosita have shown this unique signature of 511 kiloelectron volts radiating from our galaxy's core, meaning that electron and positron pair annihilation is happening inside our galaxy core as a matter of observational fact, and everyone is at a loss to explain it. But here we are able to explain it using our idea of two subverses, where each is the parallel opposite of the other, and here we are stuck in between. Of course, a discussion will more properly unpack in yet another future episode. As a final point before wrapping this episode up, we are actually able to see these two subverses. As we so carefully noted, the level of the vacuum energy inside these subverses is much higher when compared to that of our universe. The subverses, Higgs field, being in a higher metastable state as compared to our universe. Meaning, if the subverse were to emit radiation, it would be in the high energy band of the electromagnetic spectrum, because the electromagnetic field of the subverse is compressed down with respect to our own. The reason the subverse is leaking energy comes about because the subverse is expanding inside our universe. Yet another subject for yet another future episode, but to say it derives from Noether's theorem and the conservation of energy inside an expanding universe. Known as Fermi bubbles, observations from the Fermi X-ray Space Telescope, hence the name, form two giant structures in the intergalactic void in the northern and southern regions adjacent to our own Milky Way galaxy. These structures, spanning 50,000 light-years in length, glow in the gamma ray length of the electromagnetic spectrum here in the region that astrophysicists would expect these dark matter halos to be located. Observations of these Fermi bubble structures in turn have been tied directly to our supermassive black hole Sagittarius A star. Then, in turn, we have these Rosetta bubbles measuring 50,000 light years in length. Like the Fermi bubbles, these were identified using the Rosetta Space X-ray Telescope. Again, like the Fermi bubbles, these structures span 50,000 light years in length, glowing in the X-ray part of the spectrum. So effectively, the observation of the Fermi bubbles and Rosetta bubbles is reproducing the same result, showing that there is a massive structure in the polar intergalactic void adjacent to our own galaxy. Here we see evidence of these child subverses glowing in the invisible end of the spectrum. The dark matter is not so dark after all, but just at the extreme end of the spectrum, coming from the raised vacuum energy within the region of these child subverses. So, with one explanation, our idea of entrapped manifolds, we are able to give reasoned explanation and answer to the questions: how to resolve the black hole information paradox, why is the Higgs field measured to be in a metastable state, how spiral galaxies came into existence, why galaxies came to have a dark matter halo, what exactly dark matter actually is, why is dark matter cold, what caused the Fermi and Rosetta bubbles, what is the source of the 511 kilo-electron-volt gamma rays emitted from our galactic core, and what caused the formation of the long filaments of synchrotron radiation at the galactic core. Going beyond this, we have seen how our idea has the ability to shake the core of particle physics in our exploration of Schrödinger's cat, and how entrapped manifolds entrap energy in a higher vacuum state, just as particles like the electrons and protons do, giving them mass. The only problem I have with this idea in total is that it is just so damn effective at explaining the observational data, as I try and say to myself, try doing an episode where you don't end up destroying all the mysteries of physics. Until next time.